We now discuss the solution of a problem from the section Differential Equations, and the problem is on local extrema of a solution of a differential equation. This question has appeared in JEE Main examination held on 25th July 2021 in the morning shift. The problem is, let y is equal to y of x be the solution of the differential equation dy by dx is equal to 1 plus x e power y minus x, where x lies between minus root 2 to plus root 2. Minus root 2 less than x less than root 2, and the initial condition is y at 0 is equal to 0. Then the minimum value of y of x when x belongs to the open interval minus root 2 to root 2 is equal to. The four options are given to us. We now discuss the solution of that given initial value problem. So we are given the differential equation and the domain where the solution should lie, that is x belongs to the open interval minus root 2 to plus root 2, and the initial condition y at 0 is equal to 0, and that is why this is called the initial value problem. So first, let us consider the given differential equation. Dy by dx is equal to 1 plus x e power y minus x. Let's call this equation as 1. Multiply throughout by e power minus y. Then we will get e power minus y into dy by dx is equal to e power minus y plus x into e power minus x. Call this equation 2 and put e power minus y as u. Then differentiating, we will get minus e power minus y dy by dx is equal to du by dx. Substituting in the above equation 2, then the 2 becomes minus du by dx in this place is equal to u plus x e power minus x. This will imply du by dx plus u is equal to minus x e power minus x. Let's call this equation as 3. And look at this differential equation carefully. We see that it is of the form du by dx plus p of x, a function of x, into u is equal to q of x. What is this? It is a first order linear differential equation. And to find the solution of it, we find the integrating factor. The integrating factor is equal to e power integral p of x dx, and the general solution is given by u into integrating factor is equal to integral the right hand side q of x multiplied by the integrating factor and integrate with respect to x plus c, where c is the constant of integration. In our case, the integrating factor is equal to e power integral px dx. Px is the coefficient of u, that is 1 only, that is equal to e power integral dx, that is equal to e power x. Thus, the general solution of this equation 3 is u multiplied by the integrating factor e power x is equal to integral into q of x, the right hand side, minus x e power minus x into integrating factor e power x dx plus c. And we continue in the next slide. So that is our third equation, and we have substituted u is equal to e power minus y, and we got the general solution is this one. So minus x e power minus x into e power minus x. So this will be minus x only. The integral minus x will be minus x square by 2. So for u, we have substituted e power minus y. U e power minus y into e power x is equal to integral. This we have integrated. We got minus x square by 2 plus c. This will imply e power x minus y is equal to minus x square by 2 plus c. To evaluate c, we use the initial condition. Y at 0 is equal to 0. That is, y is 0 when x is 0. Given y is equal to 0 when x is equal to 0, we substitute in this, we get 1 is equal to c, and we get the solution. That solution is called the particular solution. Substituting c is equal to 1 in this, the particular solution is e power x minus y is equal to minus x square by 2 plus 1. So taking the logarithms on both sides, x minus y is equal to logarithm of 1 minus x square by 2 to the base e, and that is y is equal to x minus logarithm of, LCM is taken, 2 minus x square by 2 to the base e. This is the required solution of the given initial value problem, for which we have to find out the local extrema. We have the solution. To find the minimum value of y of x, x belongs to minus under the square root of 2 to under the square root of 2. So we compute y prime x is equal to 1 minus 1 by 2 minus x square by 2, that will be minus 2 by 2 minus x square, and 2 minus x square by 2 with respect to x is minus x, and take the LCM, we will get 2 minus x square plus 2x by 2 minus x square. Minus is taken out, we get the numerator x square minus 2x minus 2 by 2 minus x square. And to find the maxima minima, we have to compute the first derivative and equate it to 0. Then we get the critical points. So now y prime x is equal to 0 will imply x square minus 2x minus 2 is equal to 0. That is a quadratic, and we have the solutions x is equal to minus beta plus or minus under the square root of b square minus 4s by 2a, and that is computed. We got 1 plus or minus root 3. These are the critical points. Let's call alpha as 1 plus root 3 and beta as 1 minus root 3. And look here, 1 minus root 3 is 1.73. Everybody knows 1 minus 1.73 is approximately minus 0.73, and 1 plus root 3 is greater than 2. So note that beta belongs to the open interval minus root 2 to 2, because it is minus 0.73, which will lie in this, and alpha does not belong to that interval because alpha is greater than 2. So now, with the question what we are asking is beta a point of local minima? And if so, find the minimum value. That is the problem. Now, many of the students, they compute up to this, they find beta belongs to this interval, and anyway the question is asking about the minimum value of the solution of this. So there is only one point. So they will find the value of y of x at beta and they will get the answer. So that's it. They don't go for the testing of local minima or anything like that. So anyway, because I will be normally talking about the procedures and the strict procedures. So I will show you how people will compute the local extrema. To do that one, we will recall a test called first derivative test for local extrema, which is very, very important. Let f be a function, continuous and differentiable at every point in some interval containing c, except possibly at c itself. So at c, the exception is allowed. Now, suppose that c is a critical point of f. Moving across the interval I from left to right, 1. If f prime changes from negative to positive at c, f prime changes from negative to positive at c, then f has a local minimum at c. Now, second one, if f prime changes from positive to negative at c, then f has a local maximum at c. 3. If f prime does not change sign at c, that means both sides of c is either positive or negative, that is f prime does not change sign at c, then f has no local extremum at c, and in such a case the point c is called the point of inflection. So we will now use this first derivative test here. We have the solution, the first derivative, and we have found the critical points, and we have found beta belongs to the interval. So this is the interval minus root 2 to plus root 2. This is the graphical representation, and beta is minus 0.73 somewhere here. You take a point immediately next to beta, very close to it. In our case, minus 1 we have chosen, and to the right of it, the integer, the 0 will be little closer to it, therefore we have considered 0. So we will calculate now y prime at minus 1. We have substituted x is equal to minus 1 days, and we have evaluated and we have found it is negative. So at minus 1, so negative y prime at 0 we have computed, and that is greater than 0. That means moving from left to right, what we see is f prime changes sign from negative to positive while crossing beta. Therefore, we have a local minimum at beta by the first derivative test. Observe that y prime x changes sign from negative to positive as x increases through the point beta. Therefore, by the first derivative test for local extrema, beta is a point of local minima. So what is the minimum value? The minimum value is given by y at 1 minus root 3. That is y at beta. That is beta minus logarithm of 2 minus beta square by 2 to the base e. You compute and you will get the answer as 1 minus root 3 minus log of root 3 minus 1 to the base e. So let's look at the options. So our answer appears again as the option 1. So therefore our final answer is option 1. Option 1 is the answer for this question. So the discussion is over. But however, instead of the first derivative test for local extrema, sometimes people use second derivative test for local extrema also. So I will discuss that also now. The next slide is intended for that. The second derivative test for local extrema. We have y prime x. Y prime x is minus x square minus 2x minus 2 by 2 minus x square, and alpha and beta are the solutions for this polynomial. So therefore that we write it as minus x minus alpha into x minus beta by 2 minus x square. It will have an advantage of writing like this, and let's see, y double prime x you compute using the quotient rule, and substitute x is equal to beta, y double prime beta. So the advantage I will show you, 2 minus beta square into beta minus alpha remain, and beta minus beta will be 0. In this, beta minus beta will be 0, all will be 0. So that means it will be an advantage for you. So note that 2 minus beta square is greater than 0, beta minus alpha is negative. So this is minus 2 minus beta square is greater than 0. This is negative, and this is anyway positive. It is positive. So therefore the second derivative test for local extrema says y of x attains minimum at x is equal to beta, that is equal to 1 minus root 3, that belongs to the interval. So the minimum value is y at 1 minus root 3, that is y at beta, that is beta minus logarithm of 2 minus beta square by 2 to the base e. So we get the answer. So that's our required answer, and this is the usage of second derivative test for local extrema. So the students, for testing the local extrema, you can use the first derivative test and the second derivative test also according to your convenience. So that is the discussion of the solution of the problem. It's on the local extrema of a solution of the given differential equation. I hope that you have understood the solution of this problem, and I am sure you will work out some more problems in this direction. I wish you all the best. Thank you.